development of soil mechanics in the first class, and what is soil, how soil comes from, right? And then we stopped here, soil particle size. We said that soil particle size is actually important. You may have no idea about why it is important now, but later if you learn the physical property or mechanical property of soil, then you will know why soil particle is so important for soil. So depending on particle size, soil are always classified as either gravel, sand, silt, or clay. And we usually say that silt and clay are fine soil. That is, these two kinds of soil contains a lot of fine particles, small, very small particles. And sand and gravel, they are chaos soil. So here gives, based on different code, the grain size for gravel, sand, silt, and clay. But you can see that they are similar actually. And distinguished size for gravel and sand is about 2 millimeter. For sand and silt is about around 0.05 millimeter. For silt and the clay, it is about 0.002 millimeter. 0.002 millimeter, it is about micrometers. Right? It is very, very small. So you can't see actually clearly the particle. If put one particle in a white paper or a sheet of paper, you actually can't see it because it is very small. You can see soil because a lot of particles get together. So you can see this is a pound of soil. So in here is gravel. The size of gravel is usually higher than 2 millimeter. So you can see 2 millimeter, you can see 2 millimeter particle, right? Even sometimes for sand, less than 2 millimeter, right? But for silt and kaolin, you need to put a lot of particles together, get a pound of soil, then you can see it clearly. So as I said, those particles in here and those particles in here for the silt and kaolin, kaolin is a kind of clay. It's a very special clay. So the clay particle in kaolin soil is almost 70 or 80, 100%. So kaolin is definitely a kind of clay. And why this? You can see some big particles in here and in here. Because those particles is not the origin particle. It's just some small particles stick together under some water or some stick stuff, right? So, but gravel and sand, as I said, even you press it, you compress it, it can't stick together. It can't stick. And sometimes for sand, maybe you got a pound of sand, you compress it. It can be like a big gravel or a big particle. But as long as you push it, give a little bit force, it will break, right? For sand. You may try this near to sea in other place. So that means gravel and sand this kind of soil can't stick easily together. Why? This is because silt and kaolin have fine particles, actually clay particle inside. For silt soil, it always contains about 20% clay inside. In here, I say contain, it means the particle size shape. For example, for a silt soil, in here, this is loess, a kind of silt soil. The sand particle have account about maybe 5% in this kind of soil, but the clay accounts about 20% in this kind of soil. The other parts is about silt particles. So this is why it is a kind of silt, because silt particle range accounts the most in this kind of soil. So why fine particle? Why the soil have fine particle? They can stick together. This is what we will talk about in this class, the clay minerals. The clay minerals is important to clay. As long as a kind of soil, a soil have clay minerals, they can stick together. Of course, the clay mineral must have, how to say, enough percent in the soil. You can't say that it have clay minerals, then it can stick together. It can be like silt or clay. No, because for sand, sometimes there are some very, very fine particles attached on the big particles of a sand. Yes, of course, it has some clay particles, but it's not enough to get sand soil stick together. So, clay minerals, it is a little bit complex in here. In here, it's something like chemical stuff. So in here, actually, this and this is just a clay combined form. It's like how to say? We call it. Let me check the word. We call that. These are the small element for a clay mineral. So clay mineral in here, it forms by this, and this is the basic element for a clay mineral. And those two elements that are combined on a different form to form a sheet like this and a sheet like this. It's something like chemical stuff. Right? But this sheet, again, they can combine in different forms. In this kind of form, in this kind of form, in this kind of form. So these three forms are the main clay mineral combination form for those elements. The three most widely used clay minerals are this is kaolin and illite and mentamorelate. These three together. And we have kaolin soil. We call it kaolin because most of the clay mineral is kaolin. We call it kaolin. And illite, we have no clay soil called illite. If a clay with a lot illite, we didn't call it illite. We just say this is a clay soil with an illite of how much percent, something like this. Because kaolin is very, very common in practice, so we call kaolinate, kaolin. And we have more mentamorelate. The chemical looks like this. The element combination looks like this. So in here, it's just introduce three very common clay minerals: kaolinate, illite, and mentamorelate. These three clay minerals. So for clay soil, in a clay soil, sometimes we call it clay because it has kaolinate or illite or mentamorelate. It's not, sometimes they contain these three minerals, sometimes contain just one, sometimes contains just two. So it depends. But as long as it has clay minerals, we call it is a kind of clay. Of course, at this time, the clay will have over 50% particles in this kind of soil, so we call it clay. But it may have different minerals. And the difference for those three combination form is in the specific surface. If those elements get together, form a different sheet, those sheets combined together form different shape like this. So they will form a different specific surface. So specific surface, in here it is you can see it is the surface of a particle. The surface of a particle together. In here you see if this is a big element for manganate, this is a big element for elite, this is a big element for coordinate. You can see the surface is much bigger for manganate than kaolin, right? So the specific surface for kaolin is 50, and for elite is 80. For metamorinate is 800. This is a unit for the specific surface. So why we mention specific surface? Specific surface is that you count every single surface area, the surface area of every single particles. So that it's like that. You spread all the particles together and the surface of the particles. If the surface is large, then that means the soil can absorb more water, right? If you have the same, the same weight of soil, if the specific surface is higher for this kind of soil than that kind of soil, that means the higher surface, the specific surface, the more water that this kind of water can absorb. So that it is maybe the limit, the liquid limit or plastic limit will be high for this kind of soil. This is why we mention specific surface in here. So just to keep in mind that kaolinite has a less specific surface in these three clay minerals, and the metamorinate has the most higher specific surface, about 800 in these three clay minerals. So because the clay minerals can absorb the water, because the big, the huge specific surface, it can absorb the water. So as long as more water attached in the particles, if you stick two particles together, they can become an aggregate. Okay? But we have no water. It's not enough to stick them together. The water can attach on the clay minerals. So why the water can attach on the clay minerals, can attach on those particles? Because of the charge because a charge on the surface of those particles. So for clay mineral, it is a mineral. It always have a negative charge on the surface of soil particles. And you know that this is the chemical for the water, right? So water are dipolar, and water and clay then can attract together. This is why clay mineral can attract water to stick on the surface of the particles. So the mechanics of attraction between the water and the clay shown in this figure, you see. In the surface of the particle, it can attract more water element. As long as the distance is away the soil surface, then you can attract less water, and again and again and again. We call actually this is a diffuse double layer. So that is the charge on the surface of the particle is larger than away the particle, right? So if close to the particle, you'll find more water. Of course, this is in very small size. You can't see this ice. You may see this micrometer, something like that. But away of the soil particles, as long as the distance increase, so the cations will be decreased. That is the charge. Charge will be decreased. This is a diffuse double layer and the clay mineral in here. So the thing actually it's like that this part is different. It's totally nothing to do with the mechanical analysis of soil. But in here we introduce clay mineral particle first, because we will talk about the liquid limit, plastic limit later. It relates to the clay particles. Yes?
So do all types of soil contain a percentage of clay minerals?
All kind of soil. Yes, if you take the particle size distribution, all kinds of soil, for example, gravel, sand, silt, and clay, they all have clay per particle in a percentage. Maybe for gravel, it's less than 1%. You can even ignore this. This is why we call it, because they always have very small particle attached on a big particle, right? For gravel in here. If you wash the gravel, sometimes if you use the normal way, the shaping the sieves to analyze the particle size distribution, actually you got nothing for clay percent. But if you wash the gravel, you will wash the small particle from the surface of gravel particle, big particles. So that means it also contains some clay, but now the percentage of the clay is very small compared with those gravel percentage. So we can ignore it. So now the particle of clay in gravel soil actually does nothing to do with the mechanical properties of this kind of soil. So the same actually with sand. We actually distribute, we call this is gravel, this is sand, this is silt, this is kaolin. It's not because there is only gravel particle contained in this kind of soil. No, it's because most of the particle size in the range of gravel, then we call it is gravel. And for silt, if you do the mechanical analysis in here, you got the particle size distribution, you'll find that for a silt soil, it has some particle of sand, maybe around 2%. It has silt around maybe 60%, and it have clay around maybe 30%. But because the silt percent is about 60, it is much larger than sand and clay, then we call this kind of soil a silt. So for actually each kind of soil, it always have gravel. Sometimes no gravel, but sand, silt, and clay, yes, they do have. But sometimes, because with the other sand or kaolin or clay, the percentage is very small and can be even neglected. So we call it is silt. So and then let's say the mechanical analysis. So in here, we say that we define soil, gravel. This is just a particle size classification. But how we can define a soil? If a soil is gravel, sand, silt, or clay, you need to know the particle size distribution, right? As I say, for a soil, it can't be only have one particle size. It always have a range of particle size. So we need to know the particle size distribution along the grain size, right? So this, we call this a mechanical analysis of soil. The results of a mechanical analysis of soil is actually obtain the particle size distribution curve we call PSD. Then let's say mechanical analysis is the determination of the size range of particle present in a soil expressed as percentage of the total dry weight. So the two most common methods we use to define the particle size distribution of soil are sept analysis for particle size larger than 0.075 millimeter in diameter, and a hydrometer analysis for particle size smaller than 0.075 millimeter in diameter. this is the sieve analysis. This is the sieve analysis. Sieve, you know sieve, right? So the sieve will have different opening in here. You see, this is a big opening, and a less big opening, and a small opening. So those a pile of sieves, they have different opening. The opening is big. The size of the opening is larger, and is small in the bottom, is larger in the top. So it actually decreased gradually from top to bottom. So actually, as long as you shake the sieves, so different size of particles will retain on different sieves, right? So finally, as long as you you weight the dry mass of the soil on different sieves, then you go to the dry weight of the different region particle. But for sieves, again, you never go to a very, very fine sieve, right? So it have a limit. The limit is about 0.075. So if the soil, if you want to get the distribution less than 0.075, so now sieve analysis with sieve, it may not work anymore because now it is very, very fine. The sieve analysis is not work. So we use hydrometer analysis. The hydrometer analysis is something like this. It is based on the weight of different particles. So, how to say, a heavy particle will stick to the bottom of the bottle more quick than the fine particles, the light particles. So based on this, we do the analysis of the particle size less than 0.75 millimeter. This is hydrometer analysis. So this is the two methods we used in laboratory to do the mechanical analysis of soil. Then let's see how to do a sieve analysis. So we will have homework in here in the sieve analysis, and definitely examination question in sieve analysis, because particle size distribution is important for soil. And in laboratory, in most cases, we go to the particle size distribution with sieve analysis. And it is a basic method to do the mechanical analysis. So sieve analysis consists of shaking the soil sample through a set of sieves that have progressively smaller opening. To perform the analysis, the present soil passing through a certain sieve is measured and plotted on a semi-log graph to produce the particle size distribution curve. You see, this is a sieve with different opening, right? So for different standard, different code, the sieve opening is already tells you. In here, the final analysis, we will got a plot on a semi-log graph to produce particle size distribution curve. It is a curve. In the x-axis, it is particle size. The particle size actually now, depending on the opening, right? So if the opening is bigger, so the particle reaching on this sieve will be bigger. So this particle size after the analysis, after the sieve analysis, actually depending on the opening, and the percentage of passing can be calculated from the mass of the soil reaching on the sieve, right? So this is perform the mechanical analysis. The presence of soil passing through a certain size of sieve is measured percentage soil, that is the y-axis, and plot on a semi-log graph to produce particle size distribution curve. X-axis is actually the opening. So let's see, based on a US sieve size with number designation. This is the sieve number from 4 to 400. So the opening gives you in here. It decreases from the top one in here to the bottom one to here. Right? So it is a lot of sieve. But we do not use so many sieves in laboratory. Sometimes we pick 4, and then we pick 10, and then we pick 80, and then we pick 40. We pick some of them, but it distributes evenly in those sieve number. We not use all. It is very a lot. It is very high. You can't do a very good sieving. And after sieve, you choose some sieves with different opening, and you put them together. You pull a certain mass of soil. For example, you pull 1 kilogram of soil to the top one. So the top one have the most high, or the biggest opening in the pile of sieves. So the small size will get down to here. In here, it is the smallest. And the bottom one is not a sieve, it is actually a pan. It will collect the particles less than the opening in here, right? And you put 1 kilogram of soil into the top sieve, and then doing the shake. You don't have to shake yourself. You have this kind of machine. It is ultimately. Then you start it, just start to shake. And the sieve is usually, it lasts for 15 minutes. And after the sieve, you stop it, and then get down of those sieves from this machine, and to measure the mass on each sieve. The mass on here, the mass of soil in here, the mass of soil in this sieve, in each sieve. You got the mass, right? And you know the total mass is always 1 kilogram. Yes, it maybe have some loss during the sieve analysis, but it is not a lot. And the total mass is 1 kilogram. You know each mass for each sieve, right? You know the mass for each sieve. Then you know the percent, right? You can calculate the percent. As long as you got the percent, you got the opening. The opening actually is the particle size of the x-axis. Then you can go to the plot. We will do example in next class. And here, during the analysis, F is the percentage. So how to calculate the percentage? The percentage in here as you know, you got the M in each sieve, but it is not that. The percentage is MI divided the total M. This is not the percentage. It is not the percentage because the particle size distribution, the percentage in here is actually a constant. Fine. So you see in here, actually, it is accounted the accumulated percentage. It's not only 1%. It's the accumulated percentage. it will go from 0 to 100%. So it is accumulated percentage. It's not like that you got MI and then use MI divided MT. You got the percentage for just only one range of particle, right? But in here, the y-axis is the accumulated percentage in here. So we use actually this equation to calculate the real percentage for on each sieve. So that means, for example, for the top size, for the top sieve, you got, of course, 100%, right? Because all of the soil together with this with the mass on these sieves can all count the total mass, total mass of the soil. They can all pass the first one, right? And if you accumulated the mass on the first sieve, then you got 100%. And then if you account the second one, you need to account the one, those mass that from the bottom one to here, actually just minus the mass in the top one. So finally, the equation actually is in here. We will definitely do an example on next class, then you will know this. And as long as with this equation, as long as you know M1, M2 to MA, and then you know the total mass, then you can calculate the percentage. And the particle size, it is actually depending on the opening. So you know the x-axis and y-axis, and then you can plot the particle size distribution curve based on sieve analysis. And later we will give you an example to see how to plot the PSD curve. And then we move on. The hydrometry analysis actually is based on the principle of the sedimentation of soil grains in water. When a soil is dispersed in water, the particles settle at different velocity depending on their shape, size, weight, and velocity of water expressed by this equation. And this equation is proposed by this guy. So you don't have to remember this equation. In here, hydrometry analysis just to let you know that when you want to analyze the particle distribution in a very, very fine soil or under the particle size of 0.075 millimeter, you need to use hydrometry analysis. And if you check the code, they'll have procedures for a hydrometry analysis in laboratory. Just follow the procedures, then you can go to the particle size distribution curve. But for sieve analysis, because you cannot directly go to the PSD curve, then you need to do the analysis. So this is the hydrometer we use in laboratory. Usually what we do is to put the hydrometer in in a bottle. This bottle contains soil and water. The soil particle will disperse in the water. We have a break.